So, starting the lecture on vectors and databases. This is a continuation, we can say, of the previous lecture on rasters. So let's start with a recap of rasters. We have a starting point that is perhaps well defined, and then from this starting point we add data in a well-defined grid implicitly. So we just keep adding on a piece of data that covers a particular area. This area is defined in a regular grid fashion, usually a grid fashion, at least in a raster. We have a certain number of columns and rows. Each cell has a particular size, and the information is laid out. As I said, the positioning of this is implicit. We start counting from our fixed point up here, and then we just add the data onto it. And then after a certain number of columns that's been defined, we then change to the next row. That change is defined by the size of the cells in the Y here, and then start adding the data on. And there's one piece of data per cell, per pixel, depending on which type of data we're talking about. And there has to be a piece of information, no data or a piece of data, something that says something about that area. And each cell knows nothing of its neighbors. They're ignorant of each other. The data exists on its own at that location, an implicit location. So that's raster. What is vector then? So if we look at, this is a raster image, so we have pixels rather than cells here. It's an aerial photograph. And then we go over to this side, and here we have our vectors. So here we have some colors. We can interpret this image, and so we have some trees and some houses and some roads. We can see that, but there's nothing in this image that says these are these particular types of objects. It's our brains in doing that interpretation from the colors and the spatial relationships. Whereas in this, there is there are clearly defined boundaries, marked out objects that claim to be certain things, in the sense that there's a database connected to these objects, giving that information. So that's our vector concept. But what is a vector? Let's just start from some very basic concepts here. It's a word we've borrowed from mathematics. So a scalar object is just something, a size. In this example that we're given here on the screen, 20 degrees centigrade. That's just the size of something, or a distance, so 10 meters. Whereas a vector, we have a direction as well. We've taken this sort of model, as it were, of data with size and direction, and we've used that word, kind of abused it a little bit. So we define a particular data type as being a vector because it has position. And so position in a coordinate system, we can think of as, in this diagram down here, we have a direction from our origin, 0, 0, along a particular direction, a particular distance, we come to a point. So that creates our point here. So a coordinate can be considered as being a combination of size and direction. That's why these are vectors. And we can combine our points into lines and then lines into polygons. And these are the objects. All of these points, lines, and polygons are objects that we use in our vector format in GIS. So these things are, as I said, objects. They in the sense that a computer can have things actually existing, because it's only a digital medium, but we have a thing, we have a point, it is there, it has definite boundaries with qualities, attributes. It's not this kind of diffuse thing with rasters where you just have a particular amount or classification of something existing in a particular, in a cell, in an area, and you don't know where that ends, you don't know what it actually really is. Whereas in a vector we have, here is the thing, the object you are looking for is at this place, and it has a particular size. Whether that's a point, line, or a polygon, that defines the spatial extent of it, but it definitely exists there, if we're existing in a little computer world. The qualities, the attributes that it actually has, are the same across the entire object, which is fairly obvious for a point. A point must have the same object all over its entirety. But the same thing applies to our lines and to our polygons. They are homogeneous. They exist over the entire area or the entire length in the object as a whole, and then at the boundary of the object, that quality, that attribute ceases, and either there is nothing afterwards or around it, or we transition into something else directly. The data are thus discrete. Let's look a little closer at this. So here we have a little illustration. We have a table of data describing particular qualities, and then a map plotting out this data. So standard for GIS, spatial data, in our vector format, is that we have these qualities of X and Y, positional information. They're not usually considered to be attributes. These are sort of integral to the thingness of a GIS object, defined as having location. The Z here, elevation, can be an integral part of the position, or it might be considered an attribute. This is not there's no consistency in how this is applied. There are 3D formats and 2D formats. Quite often you will find a lot of GIS data is actually 2D, so we have X and Y, and then the Z is perhaps either just not stored at all, we have kind of flat data on a map, or it's an attribute so that it doesn't have, we don't directly access the geometry implied by the Z coordinate. We perhaps can transform our data to have these three coordinates, but generally speaking, in a lot of GIS work, we are looking at two-dimensional data with just X and Y. And then we have these attributes. So here we have 4 points on the map, but I have 5 rows in this table, which may seem a little odd. And we can see that this last row is essentially the same as the first row, except that the attribute is changed. So we have start, suggesting something, and then we have park, shop, and end. So this could be where I start my day, and then I go to the park, sit there, feed the ducks, and get bored with that, and then go to the shop, and then go to another shop, and then go back to where I started, which may be my home, perhaps, or some other location. So these points are defined in themselves. They have these qualities at those locations. The order in which I visit them is not defined. There's nothing else about them that I can say. From this, they just exist at these locations, and these 2 points are coincident in space. They have the same location. They are essentially not the same point. They are 2 distinct points. They exist as 2 objects in the table. They are coincident in space. That's all so far. And then I can turn this into a route. I will start walking around. We can see I start from this point here, from 100, 100, and then I go to the park, which is up here, and then onto the shop, and then to another shop, and then back to the end. So that's my route around. But my route does not possess these different qualities. The points, these nodes here, in themselves, external of the line, possess those qualities, but the line does not possess those qualities. The line is homogeneous. It is a thing in itself. It is my route. And my route is defined as going between these different locations. So I go from this point, this location here, to this location, to this location, to this location, and then back to that location. So that is my route. And we can see that the attribute for each of these points is route, because it's an homogeneous object. Well, okay. We don't really need to store that attribute because it's always the same. It is one object. It does not vary across its length. It is always homogeneous. So it is the root. We can get rid of that extra column. We really should not repeat data unnecessarily in terms of data storage efficiency, but also consistency in our logic. it's a detail point, and quite often we will find data where this isn't implemented or doesn't appear to be implemented correctly. There are for good reasons in many cases, so we need to be careful with being too critical, but essentially we should be saying do not repeat data unnecessarily. So that was points to lines. Well, what happens then? We've gone from points to lines, and we have a line here that goes around. Once our line goes back to its starting point, we can then say, well, we've enclosed an area, we've defined an area, and everything that is within that area, or potentially outside that area, is a thing, is an object, is a polygon. So we have defined this object here. This whole area becomes a thing because we have drawn this line around it. In this case, it is simply a line. We're just walking along. This may be my route. But if my route that I'm walking is the boundary of my property, and I'm defending my property, marching around it, then I've walked along the boundaries of my property, and everything within it is my property, for example. So I have an object, a polygon, to begin with, and an object because I defined it as being such, which is perhaps a subtle point, but let's look at the lower half of this diagram here. We have this same basic object up here, the same polygon, but then there's another polygon inside it, a polygon with a hole, or is this actually an object consisting of two polygons? We have one polygon defining the outer boundary and then another polygon defining an inner boundary. This is all one object, but we require two polygons to define it. So this could be a body of water, for example, and here's an island. The island, depending on how you view things, may not be a part of this lake. It's dry land. This is a matter of ontology for you, but we have defined this object with the help of two polygons. So the object and the polygon are not actually synonyms. Often when we're talking in GIS, we use them synonymously, polygon, object, which is not entirely correct. We really shouldn't do that, but it's easily done in the same way that we say pixel and cell interchangeably, which we shouldn't do either. But here, to carry on with this example, two polygons here, one object, the mainland and an island, for example. Sweden, Gotland. Gotland is part of Sweden. Mainland Sweden, Gotland. So this is our distinction. We've gone from the line, define a boundary to make a polygon, and that polygon we then define as an object. This is an object, this is an object, this is an object. This is a polygon, this is a polygon, this is a polygon, this is a polygon, and this is a polygon. So those are the distinctions between points, lines, objects, points, lines, polygons, and objects. So how does this apply to us in GIS? So this is a very, very crude representation of some form of reality, a very peculiar reality, but we have some object here, a map of some sort, and then we're going to put that into a database. We're going to define it as our GIS. So we've transformed each of these houses, villages, whatever they are, into a point of data. We have a road here that becomes a line going around here, and then we have this lake, presumably, here as a polygon object. So they've then been entered into our GIS. We've gone from the reality to this GIS data. And how might we be storing this? This is an example of how data can be thought of as being stored in a GIS. Points, lines, and polygons. The way we build up data often is to consider the so-called nodes. A point can be thought of as a node, but then the points along a line are also nodes. So these are the point information, discrete points of information along where we will place out coordinates, if you like, coordinate pairs where something happens. And if we look at this first table, these are our towns, and we have information about these towns, and we're pointing to them on the map here. But how do we know they're there? Well, we connect We say we want this location for that one, we want that location for that one, and we want that location for that one. We're using this ID number here, or rather this number stored under node, and we're looking in the ID column. We're saying, well, if you go to this node table and look for this number in the ID column, that's the coordinate for this point. Trivial perhaps, but actually quite important, and we'll get back to this this relationship in a minute. Similarly with the road, sometimes we make more of a job of this. So we have our road object, and it's got a name. How is it defined? Well, we say go to this table here, and that table will define the lines or one line included in our road object, which is a line object, but it could consist of several lines. In this case, we've just got the one line, and that line consists of these nodes in this order. So go and pick up these nodes here, which it does. So we go and collect all of those nodes, and that defines our line.